Thank you. Right, good afternoon everybody. First question, which I know one table has already solved some of the problem, one table already knows the answer as well. What's my name? Visitor, that's a good clue, isn't it? Reading visitor, the word Mr. Visitor, absolutely. Anybody else got a suggestion of my full name? Yes. And how did you know my name? It says it on there, isn't it? So some people have been looking around the room trying to kill time whilst they've been waiting, and they've looked at the things on the screen and they've seen my name. So that's one way you could have done it. Using your eyes, you've looked at stuff and you've gone, oh, that name on there must be that fella sitting over there. So that's good. So you've done that. How did this group from Westbourne, which is where we are, how did this group know my name? Do you know my name? Yeah. How would they know my name? Well, if I tell you that I come here quite regularly and I've taught them before, how do they know my name? Because they call me by my name, they've used it before, they've met me before. So it's a fact, it's a piece of information that they already know. So we're looking at how we solve problems, we're looking about how we work at things in maths. And one of the things we need to do is look at stuff, look at what's there, and work out what it is, and see how it might apply to what's going on. So you saw my name, and you thought, well, it must be this fella. So you made those links. It could have been, though, that I was just sitting here, I've come to do the cleaning this afternoon. I was just waiting until you'd all finished before I could clean up the room. But the chances were it was going to be me. So you worked out it out. How else could you have worked out my name? Mr. Cusbin did not introduce me. If you'd introduced me, how else would you have worked out my name? You'd have listened, wouldn't you? Okay? So you can look at things, and you can listen to things, and those two things work together to help you to develop your understanding. So you're definitely going to do quite a lot of this afternoon. Looking and listening to hopefully help you with learning. But some of the time you're going to do a bit like the Westbourne people. You're going to need to use things that you already know before you came into this room to help you to work things out. Okay? Because I couldn't do what we're going to do with a reception class. Okay? Because even though they might be equally as intelligent as you and equally successful as you in the future, there will be things that they don't yet know that will stop them doing what we're going to do. Okay? So you will need to use things that you already know. Okay, so I'm assuming that you know certain things. Okay. What do you think we might find out about it this afternoon then? There was a really nice discussion going on this table because you were about the first to arrive and you went up into the screen, and you were killing time too, looking at the screen. What do you think we might be finding out about this afternoon? What might be involved in what's going on? Yeah, go on.
The magic squares.
Right. How do you know that?
Because there's a sheet and you can see.
Oh, you can see through the sheet. Okay. You can read upside down, back to front in mirror image. Good. What about the things that you might have seen on here? Yeah.
There was pictures of history.
Right, there were some historical pictures, weren't there? So we're going to meet, or find a little bit out about that bit of history there. There was 2 pictures on there. I heard the discussion on this table. I'll speed things up a little bit, but on this table they were talking about whether it was the same person or a different person. And one of the things you were discussing was beards, wasn't it? And moustaches and who have, because they both got long hair, but is it the same person? And if you're looking at the nose, you're beginning to compare, it could be the same person, could be a different person, could be different ages. And then there was also a question, what's your name? Liber. Liber said something very early on, she just kind of looked at me and said something. What did you say about the pictures? Right, she said they look like Tudors, which is excellent. Because again, she's taken something she knows from somewhere else, something she's found out about. I guess you've done Tudors as a topic, haven't you? And found out about Henry VIII and things like that. If you've done that, you've taken that piece of information and you've looked at some new things that you've not seen before and gone, oh, that's a bit like the Tudors. Well, if I tell you, Liber, that you're absolutely correct in one aspect. That person or people in those pictures lived at the same time as you would have understood the Tudors. So the same time in history as the Tudors, those pictures. So you've taken in lots of clothes and gone, it looks like it, so it probably is. So that's good deduction, well done. Okay. But that's fine. So we're looking at, and we're beginning an investigation on magic squares. What are magic squares? And how are they magic? That might be the next thing. Yeah?
They've got numbers in them that make something.
They've got numbers in them that make something. Okay? Like that, you good use of technical language there. Good vocabulary there, summit. Yes, they've got numbers in them, this magic square. Okay? The magic part is about how the numbers work together. Okay? The square part is the fact that the numbers are going to be arranged in a square, okay? So we're going to be finding out, won't go on too long about these, but we're going to be looking at recognising and trying to understand patterns that occur in magic squares. So recognise, the infinitive to recognise means to just see it. So if I walk down the street tomorrow, you might recognise me and go, oh, that's that fella again. What was his name? Oh, Mr. Tidswell. You might recognise it. But understand goes deeper, doesn't it? You need to be able to explain why something's happening, explain your reasons, be able to demonstrate why something happens. So recognising it is good, it does this. Understanding it goes much deeper, doesn't it? Okay? So, we're going to look at a magic square. Really important word I've used there this afternoon. A magic square. What does that mean? What's the difference between you saying a magic square and saying something different?
A magic square means one magic square.
Means one particular magic square. How many magic squares could there be, though, if I use the word a? How many different types of magic square could there be? Any, okay? If I said we're going to look at the magic squares, how many magic squares are there in existence?
One.
If I say the magic square, how many are there in existence? One only. And that's a big difference, isn't it? So we're going to look at a magic square first of all, but there are lots of different types of magic square, which we'll see a little bit of as we go through the course of today. And it's quite important, when we're working with maths, we forget sometimes we're also doing literacy. And maths and science link up, and maths and music link up, and maths and all sorts of things link up. But sometimes we forget we're doing literacy, because we've just talked about the words recognise, we've talked about the words understand, and now we're talking about two really important words, a and the definite and indefinite article. A means one of a choice, the means only one. I'll do what I did this morning. Okay, I'll borrow something today, this afternoon. Okay. Would you come out, please? What's your name? Simon, come out, please. What's the difference? Would you sit on the stool, please? Okay. So I used the definite article that time, didn't I? Okay. Would you stand up again, please, Simon? Okay. Would you sit on the stool, please? I'm really in control here. It's like a computer curriculum now. I'm completely in control, Simon. Okay. Would you sit on the stool, please? Okay. Thank you. You can stand up again now. Go back across there. Have a look at these stools. Would you sit on a stool, please? What was the difference for her that time? Yes.
She had to choose between the two stools.
She had. What did it say about reception there? She had to choose between. I put 3 out there. There's another one tucked under here. She could go over here and get one if she wanted. She could tuck down there. She could go back to your own school and see if there's some stools there if she really wanted to. She's got lots of choice, hasn't she? When I say the stool, I mean only one, don't I? Thank you very much. So in maths, we have to use English quite a lot, and we have to be careful with it because we have to be able to use it correctly to be very clear on what it means. We'll see some examples of that as we go along, because we had some fantastic language earlier. It does something. And we all understand in our own minds, don't we? We all understand what doing something is. But unfortunately, it's lots of different summits, isn't it? Lots of different things. When we're talking about maths, and you know this stuff, then you've got to be clearer and clearer and clearer and more precise so that everybody else in the room understands. English is a subject that you will study about communication, about getting your message across. If you don't write your sentences properly, people don't understand you. You don't spell words properly, you're less likely to understand you. But maths is a communication subject as well. It's about getting your message across about the maths that you understand and how you can understand it and how you can explain it to people. So you need to use your language carefully. So, here's the magic square that we're going to look at. It's one of many, and this is the one we're going to start with. How many little squares are there on the big square? 9, how did you know? Just 3, 3, 3. Yes, of course, because again, you're applying your knowledge from somewhere else. If I'd asked that to a reception class, what would they have done? 1, 2, 3, and they'd have counted it, wouldn't they? Okay, because they wouldn't have immediately gone, oh, it's 3 lots of 3, which is 9. 9 is what kind of number? Special kind of number. It's got a name. It belongs to a set. We're already being magic with our squares, aren't we? Because you know that 9 is a square number. Give me the next square number in the sequence. 16. Because what is the square root of 9? What do we multiply by itself? 3. Okay, the square root of 9 is 3. What's the square root of 16?
12.
Excellent. Okay. So this is a square of 3 squares by 3 squares, so there are 9 squares altogether. What have we got around the outside of that square? Is it going to be magic because when we put the numbers in there they're going to jump around and dance on their own? No, it's not going to be as exciting as that. We're going to arrange these 9 numbers in here, and we can only use them once each. We can't have 2 lots of 4 in there or 3 6s. You've got to use each number once and once only. Arrange them on the grid so that when you add them up in this direction, each one of these makes the same total as those and those. What are all these things I'm talking about? See, I talked about language, didn't I? Okay? So I didn't give you any names. What would I call that sort of thing? A row. Okay? What direction does it go in? Sideways, that way. It's amazing how everybody models things as well. Sideways or horizontally is the more mathsy word, isn't it? So horizontally creates our rows. Okay? Or sideways or that way. Okay? So horizontally creates our rows. We've got 3 of those. What do we call the ones that go with that thing? Vertical, and we call them what? Columns. So we've got 3 columns. What do we call these ones? Diagonals. Okay, so they go from top left to bottom right, top right to bottom left. Okay. So if I've got 3 rows, 3 columns, and 2 diagonals, how many sets of 3 have I got? Nope. 8. I'm throwing lots of things quickly, you've got to process it fast. Okay, so we've got 3 rows, 3 columns, 2 diagonals, making 8 sets of 3. Each one of those sets, the 3 rows, the 3 columns, the 2 diagonals, when you add the 3 numbers in them, they will make the same number as each other. Okay, so that plus that will make an answer, and so will that, and so will that, and that, and that, and that, and that, and that. They will all add up to each time make the same total. Okay, so you're going to try to place the 9 numbers onto the grid, so that the 3 rows, 3 columns, and 2 diagonals, each one makes exactly the same total as all the others. That's what makes a magic square a magic square. Before I set you off, I'm going to give you one clue. One clue. And this is an example of how I want to respond to any time you're getting stuck or not sure about things. I will try to answer any of your questions with questions, okay? So the first question I'm going to give you as a clue is, which space, which square on the grid do you think is the most important position? Lots of hands going up for that one. Yes? The middle square. Why is the middle square so important? Yeah. Excellent, because it's included with all the other squares, isn't it? So just look at that carefully. There's the middle one. It works with a column, doesn't it? It works with a row. And it actually works with both of the diagonals. So at some point, the number in the middle must work with all the other numbers. Okay? What number do you think might go in the middle? Have a look at that set and think about what numbers could go in the middle. And there may be reasons. Yeah.
5.
5. Why do you think 5?
It's kind of a big number and a small number.
I like that. 5, because it's kind of a big number and kind of a small number. It's kind of somewhere in the... It's in the middle, isn't it? Okay, it's in the middle of the set, isn't it? Okay. So you it's got some of the properties of being a big number and some of the properties of being a small number. And the problem is, what you need to do, and remember I mentioned earlier on about hiding numbers away from each other. And one or two of the examples I've seen is some people do things like they go 1, 2, 3, 4, 5, 6, 7, 8, 9, and see how it works. Well, that means that that row's got 7, 8, and 9 added together, and this row's got 1, 2, and 3 added together. There's no chance of them ever making the same total, is there? So if you end up with groups of big numbers and groups of small numbers, you're in trouble. So if you had the biggest number in the middle, it has to work with all the other numbers, so at some point it would have to work with 8 and 7 over here. It would have to work with those, and that would already mean you've got a really big number that's very difficult to repeat with other ones. And the same would be true if we put 1 in the middle, because if we put 1 in the middle, it would at some point have to work with 2 and 3. So what we want to try to do is find ways of hiding the big numbers from each other and the small numbers from each other. So that's, I won't go too far, but I will tell you that yes, you're right, that number goes in the middle. Okay, so some of you have been trying with 5 in the middle and it's not worked out yet. Some of you have been trying other numbers out for various reasons. It's perfectly sensible before you start quite often people do say to me, oh, I think 1 will go in the middle, or 9 will go in the middle, because you tend to look at the set and go, big one, small one, middle one, and they tend to be the areas that people look at most often. So we are saying to you now, that if you haven't already worked it out, that 5 is the middle number. Then, the next little clue is to have a think about what happens with the rest of the numbers. Okay, what can happen with the rest of the numbers? Go on then.
They go into a number bond to 10.
Right, number bonds for 10. That's where I'm stopping with that clue. Number bonds for 10. So we've got that number, which we've told you does go in the middle. Then the phrase number bonds to 10 has been mentioned. Okay, who would like to have a quick guess at what they think therefore the total for each row, column and diagonal will be? Why?
Because number bonds to 10 is like if I say 7 and 3 is 10 and 5 is the middle number, so 7 and 3 and 5 is 15.
Interesting thinking. Okay, interesting thinking. Carry on and see if you can find one. If you found one, try to use ways of making another one. On a couple of tables, I've heard a really useful phrase being used, particularly with the teachers talking to the students, talking about trial and error. I know we're discussing it here, I heard it somewhere else as well. Trial and error, as somebody said, is a really valuable strategy in maths. Maths geniuses with brains the size of planets working at posh universities use trial and error. They test things out, and then if it doesn't work, they look at why it's not worked, and how does that help them to try the next one so it's a little bit better and a little bit better. It's kind of zooming in your focus. It's a bit like if you're seeing a picture and it's all blurry, and as you change the focus on the projector, gradually it becomes clearer, and your guess improves each time as to what that picture is. So your trial and error is a perfectly sensible strategy. And if you'd spent a lot of time, once you've realised 5 went in the middle and bonds for 10, you still needed to use a bit of trial and error to work out what happened. But eventually people then, they might be lucky and do it first, or they might be unlucky and do it after the third go or something. Eventually they'll put an 8 in the corner rather than in the middles, okay? Because the even numbers actually in this workout is going in the corners, and the odd numbers go in the middle of the rows and columns. Okay, so from there we've got the 8. Put your hand up if you have now got at least one magic square as a correct solution. Oh, that's pretty good. Okay, put your hand up if you've got more than one correct solution. And just like this morning, when you put your hands back down again now, I asked that, and the hands that went up for one solution, nearly all of them stayed up for more than one. Because with maths, that's what happens a lot. You work hard at something that's difficult, and you can't see the answer, and you can't quite do it, and you're not sure what's going on. And then suddenly you go, ah, that's what it does, I've got it. And then it suddenly allows you to leap forward and make lots of things, make lots of discoveries. Use that method to solve lots of questions, okay? Use that discovery to help explore other things, okay? So you've done that, you've kind of struggled, suddenly you've done it, and then you can get lots of examples. So let's now have a look at the logic that helps us to complete that. By having those 3 numbers in place, we've used logic to just get one number in. We said that the even numbers could go in the corner, so I've put that one there. And then logically, the 7 and the 9 must be hidden, and that's the only 2 places we can hide it in. We could swap the 7 and the 9, but that's the only 2 places we can put the 7 and the 9 at this point. So now, how do we go about solving it? What would be our next step logically? Okay, what would be our next step logically? Yes?
On the bottom vertically and on the right horizontally, you can put a 2 there.
Okay, so this bottom right-hand corner.
Yeah.
Okay, you've given me 2 descriptions there, and the bottom right-hand corner. Why can you put 2 there?
Because 8 add 5 is 13, and then if you add 2, it'll be 15.
Okay, that's correct. Give me another reason why 2 goes in the bottom right-hand corner.
Because you don't want a 1, 2, and 3
So you've got to hide the 1s and 2s from each other, but give me another reason that maybe ignores the 5 this time. Yeah.
8 and 2 and a number bond of 10.
Alright, so we've got our bond for 10. So we're looking for 8 for its partner for 10, and that's it, isn't it? So that's really what you were doing, isn't it? Okay? So give me the next logical step. Maybe there's more than one route through, but give me another logical step. Yes? Okay, well, which one? What are you going to do? Are you sure?
No, you have to sit that there. Is there and one has to be there. So
We've got lots of theirs going on. I bet the people at the back of the room going, which there is he talking about? There's lots of theirs going on. Okay?
the one has to be in the...
Right, come and point to where you think the one's going to go.
One's going to go down.
Right, hang on a second. Point to where the one's going to go. Right, he's struggling to tell us where that is. Now we're pointing at it, we know. Somebody tell him where it is. Yes?
Under the 8.
Under the 8, that'll do me. Think about it just generally as the grid itself, as there was no numbers in the grid. What would we call that one? We wouldn't call it Samantha, would we? What would we call that one? Yes?
In the middle square of the first vertical, in the first horizontal line.
Right, first.
Vertical.
Right, so middle square of the first vertical column, okay, middle square of the first column, or first square of the middle row, okay, so we're giving a bit better description there. So you want to put 1 there, but you said you could go there as well.
1 is a number bond for 10.
Excellent, so 1 is a number bond for 10, so it agrees in 2 ways, doesn't it, okay? It's hiding from the 2, but it's bonding with 9, so it's agreeing in 2 ways. Excellent. Next piece of logic, somebody else tell me. Have you put your hands up? Yes, you have. What's the next piece of logic? What's the next place we're going to go? So how can we find another example? What can we do to find another example? Yes? You have to shout because I'm old and deaf.
6, 7, and 2 could also go in top row, and the 3, 8, 3, and 4 could also go in bottom row, and 7.
Excellent. So we could take that bottom row, 6, 7 and 2, take it off completely, place it on the top, take the numbers from the top and place them on the bottom. What happens with 1, 5 and 9 in your solution?
They could be 9, 9.
So if I take the 8, 3 and 4 off and swap it with the 6, 7 and 2, what am I going to do with the 1, 5 and 9? Just leave it. That's sometimes a struggle, isn't it, for an answer, is nothing is the answer. He's like, I don't do anything with that. Why is he asking me to tell me what to do with it? Well, the thing you do is nothing. You don't do anything with it. Because these 3 are going to swap exactly with those 3, and those stay in the middle. It's a bit like using this as a line of symmetry and reflecting those with each other. Okay? So if you can work horizontally, how else can you work?
Vertically.
Vertically. So tell me how you could swap them vertically. Go on then.
Left and right.
So left and right column, left column swaps with right column, so 8, 1, 6 will come over here, 4, 9, 2 will go over there, so you're absolutely spot on. That would be another way of doing it. And there's another property of a square. We've looked at effectively using reflective symmetry, but we've also got another form of symmetry that a square does.
Diagonal.
You can rotate, you can work diagonally, but that doesn't work in quite the same way, okay? So we could try swapping the 8 over here, but then we'd have troubles, wouldn't we? Because what do we do with our 6 and 4? And we can swap them like that, and that can work for us. So we've got our reflective symmetry, but I'm now looking at another form of symmetry. Okay, you may or may not come across this other form of symmetry. We've got reflective where we stick a mirror on something. Yeah, this is giving clues. Turn it around symmetry, that famous bit of maths, turn it around symmetry. Rotational symmetry. Mr. Custom won't get you later now if you answer that correctly. Rotational symmetry. Imagine we put a pin in the middle of the square and we turn it. How many times can we turn a square and it still looks the same? 4. It's got order of rotational symmetry of 4, hasn't it? Okay? So we can use that. So we can rotate. So we can turn it now. So if I turn this by 1 rotation, where would the 8 end up? Which number would it replace? If I rotate it, which number would it replace? I'm rotating it clockwise, just to be clear. Which number would it replace? Yes?
4.
Okay, 8 would replace 4. What would 3 replace? Yeah?
9.
3 would replace 9, and 4 would replace 2. So we'd rotate it. That would give us another version. And then we could rotate it a second time, so this 8 would now move down to where the 2 was, and then we could rotate. We sometimes would look at that in a little bit more detail and do some more explanations about the way things work and look at the symmetry and all sorts of other things with it. Now let's move on, because we wanted to meet this fella from the Tudor period. This is the character we're going to meet. I'm going to speed things up a little bit. We're going to tell you his name. His name is Albrecht Dürer. Okay? I've told you he was alive at around about the time that the Tudors were alive. Okay? So if you've ever done any work on Henry VIII and his wives and all that kind of stuff, who's done the Tudors in school? Okay? So you know a bit about the time of life that he's alive. Why did you say, what's your name, sorry again?
Liber.
Liber, why did you say he was alive in the Tudor period?
The clothes.
Right, you're looking at his fashion, aren't you? Okay? So, you might not think I'm the most fashionable person on the planet, but you can tell I come from the 21st century. Okay? We can look at somebody's clothes in a picture like that and begin to work out clues as to where they came from in the past. And if you already knew a bit about the Tudors, you can kind of go, he looks a bit like one of those Tudors. Okay? Didn't live in England, he lived in another European country. Anybody want to know? Not Europe. Which country did he come from?
Greece.
Greece? Good idea. Why did you say Greece? Because you just thought of the first European country that came to mind. Fine. Perfectly logical. Dutch? Why do you say Dutch?
Because Albert and Dürer sounds Dutch.
Fantastic answer. Nearly right. You've used exactly the right logic. You've listened to his name, Albrecht Dürer, and you found that doesn't sound English, and it doesn't sound French, which is a bit softer, isn't it? Okay, Pierre Dürer, okay, or something like that it would be, wouldn't it? But it sounds a bit harsher. So it's nearly right.
Sweden.
Similar kind of language as well. We've gone up north to the Scandinavian countries.
German.
German is the correct answer, which is next door to Holland anyway, okay? So next door to the Dutch people. But it's the right sound, because this is Albrecht. We've got harsh consonant sounds in there, haven't we, rather than soft consonant blends that we might use in English. So Albrecht Dürer and magic squares. So he's got something to do with magic squares as well. Now, if I tell you both of those are self-portraits, what was his job? Artist, okay? So there are pictures of him by him. There he is again, another picture of him by him. We could give you a good lecture now about the importance of that painting to Renaissance art. Do you want to have that lecture right now? No, thank you very much. Okay. But very, very important picture, because it's one of the first paintings in art history when a human being, not Jesus in Europe, not a human being is looking straight out at you. In the past, all paintings of people in the past, or paintings of real people, tend to be like that, sideways on. Look at me. Not straight out the camera, look straight out the camera looking at you. Whereas artists in Europe painting Christian pictures would paint Jesus looking out at you. So it's a big shock to have a human being looking out at you like that. So it's quite an important picture. So it's dancing for you. Okay? I did this with a lot. First one to really have that painting looking straight at you like that. Yeah, first humanist painting. So we've got the information on there about Albrecht Dürer's life. So we said he was alive during the Tudors, so if you remember your Tudor dates, it overlaps reasonably well, doesn't it? Okay, yes, she's saying yes. Can't remember them, but she's saying yes. Okay, I asked this question this morning, I'm going to ask the same one again this afternoon. What's the next question I'm going to ask you? You know, because I asked you that about other people. And catch you out. What's the next question I'm going to ask you? Go on then, tell them what they're going to do.
How old was he when he died?
How old was he when he died? Okay, how old was he when he died? Write your answer down, have a go. Let's just go around the room first of all. One answer from each table. 56. 57. 57. 57. 57. 56 and 57 on that table. 57.
56.
Oh,
56.
oh, controversy. Yeah, that's it. It's because when you sack them. Yes. Okay. Okay, controversy. We've actually got. You've overdone it that time. We've actually got two main solutions, and one that I'm going to ignore. Two main solutions there. We have people saying this answer. Helps if I think of a pen, doesn't it? We've got some people saying this answer, and some people saying this answer. You can see they're pretty close, so they must have been using actual maths to work it out, which is good. Okay? Sometimes people just guess randomly and go, oh, he looks as though he was about this age. So it's one of those two is correct. So somebody please tell me how you go about solving this. Yes, go for it.
First I got the two dates,
Yeah.
1528 and 1471,
Yeah.
and I put the larger one on top, and I took away the two numbers from each other and I got 57.
Okay, so you've done a subtraction. It goes back to what we're going to talk about tonight, so didn't it, about actual calculation methods. So you've done a subtraction, column subtraction, decomposition. Okay? I don't think I can bother with that. Too many things to trip over at this stage. Yeah? But that's fine. You've got the right. You've got an answer.
If you do 1471 to 15,000, you get
1500. Yeah. 1500. Yeah.
29,
You
and then
correct.
29 and 28 is 57.
Why do you say I have 28?
Because 28 years after 1500.
Okay, because we've got to go from 1500 to 1528. That's kind of how I do it in my head with those dates. Is you see the difference between having to set it out as a formal written method? I've jumped 29 to get to the next 100, and then another 28 to get to the 1528. I can now add those two together. What do they make when we add them together?
57.
57 is the correct answer. So 29 plus 28 equals 57. Okay, put your hand up if you got 57 as the correct answer. So there's fewer people putting their hands up this time than they were doing earlier. Those people have put 57. Okay, so you're feeling quite smug now, aren't you? Or some of you are feeling slightly nervous because you've started taking your hands back down. Okay, so that's the difference between the 2 years. However, how old was he when he died?
56 because May's after April.
Okay, it's
No,
50.
April.
Okay, it's 56 because he was born in May 1471 and he died in April 1528. So if you'd spoken to him on April the 6th, he probably wouldn't have felt very well, but if you'd spoken to him on April the 6th, 1528, and he said, excuse me, Albert, how old are you? He'd have said, I'm 56. Now leave me alone, I'm feeling poorly. Okay? Because he had not yet got to May and had not yet reached his 57th birthday. So the problem with that is, all of those of you who got 57 did all the maths bit right, but what you forgot was to take that answer and apply it back to the original question, the original problem, which had an extra piece of information in it, which changed the final answer. That's where he lived, was Germany, and he travelled down to that country, Italy, to find out about all sorts of things to do with that, okay? And he went and visited a very, very famous Italian Renaissance artist who was called... How do you know that?
Because he painted the Mona Lisa and he was Italian.
Look at this. Okay, art history lessons going on there, okay? Excellent stuff. You're completely correct. So, the famous Italian Renaissance artist Leonardo da Vinci, or Leonard da Vinci, okay, he was around at the same time as Albert Dürer, and they were friends. They would write to each other and share ideas. And both of them were what we call polymaths. They did lots of stuff. So they did bits of science, they did bits of art, they did bits of music, they did bits of all kinds of things, and they shared ideas with each other. So, how old was his mum in that picture? 63. Not 1,514, but 63. Okay, you see the clue in there. So again, you're using your eyes to look at clues and work things out. Okay, tough life in those days, wasn't it? You did well to get to 63 in those days, but you also look like that. You looked about 163, didn't you? Okay, and I've pointed out that number at the top. So what year was that picture done? Yeah? Yeah, finish on. 1514, okay, that's the year of that picture, okay? The importance of that being that this next picture I'm going to show you was done in the same year. It's another one of these etchings, okay? Look at the amazing skill. And you have to do everything back to front when you do an etching. You have to draw back to front because then when you print it, you get a mirror image. So the words at the back have to be done in a different way. Now this picture is called melancholia. The word melancholy means miserable, really. So it's a good word to use in your writing as well, to mean miserable. And you can see that miserable angel. We mentioned it very briefly earlier. What does that have to do with maths? Anything you can see on there that has to do with maths? Yes?
Shapes.
Okay, so there's some geometric shapes on there, isn't there? There's things like spheres, and then this kind of thing that we could probably find out what its name was. And then there's, you might see some weighing scales on there, different bits and pieces that you could link into maths, and compasses she's holding in her hand to measure things with as well. Okay, dividing them. Look carefully and see if you can see anything to do with number that might link with what we're doing. Okay, yes? Square in the background. Okay, that's it. Just pull it out a little bit. There's a square in the background. That comes from the picture. Okay, you immediately said it's a magic square. Why did you say it's a magic square? Because it'd be pretty daft, wouldn't it? I mean, to do all this stuff about magic squares and then show you a square that wasn't magic. Okay, so which year did I say the picture was drawn? 1514. What do you notice about it, therefore? Yeah? It's got the date on it. Look at the bottom row there, 1514, it has the date on it. This, not only was the first one to do those face-on pictures, one of the first people to get that kind of thing going, but this was the first time that a magic square had been seen printed in Europe. Okay? They were originally kind of discovered or come up with by the Chinese, but this is the first one we've got that came into Europe, that was seen in Europe. This is a magic square, but it's different to the one we had before. How is it different? Yes?
It's got 16 squares in it.
It's got 16 squares rather than 9. It's a 4 by 4 magic square. But again, it is a magic square, so each row and each column and each diagonal add up to make the same total. What is the total this time? What is the total this time?
34.
34. You were already anticipating that question, weren't you? Okay, so you'd already started working out. So each row, each column, the two diagonals add up to 34. There are 10 of those, 10 sets of those. Okay, 4 rows, 4 columns, 2 diagonals, so there's 10 sets. And it includes the date at the bottom. But this magic square is especially magic. It is incredibly magic. There it is. You can see the numbers more clearly this time. Not only does it have 4 rows, 4 columns, 2 diagonals that make sets of 4 to 34, but it has over 80 combinations of 4 numbers that add to make 34. Okay? So what you're going to do in a minute is you're going to have some versions of this that will help you, and you're going to explore the numbers on here, putting them together on the grid, not taking them off the grid, but putting them together on the grid, looking at how they're arranged to say these 4 numbers, put those together, and they make 34. I'm going to give you one example to get you started on that. So if we pull out the 4 column numbers, 16 and 13, 4 and 1, we pull out those 4 corner numbers, that's what we're left with. Now, what does 16, 13, 4 and 1 make? What's the total? Now, some people might go, it's bound to be such and such. Yes? How do you know?
13 plus 29.
Yeah.
13.
Perfect answer. 16 and 13 is 29. Nice and big numbers out of the way. Plus the 1 makes life easy, turns it to 30. Stick the 4 on the end of the 0, makes it 34. That's one perfectly sensible solution. The version I often use is 16 and 4 immediately gives me 20. And 13 and 1 gives me 14. So I've got 20 and 14, which makes 34. But that's not the only way to solve it. Lots of ways of doing it. But that's what I mean. That's a set of 4 numbers in a recognisable position on the grid, a position you could describe or notice, that gives the total 34. So what you're going to do is you're going to look at the grid and see what other patterns you can find. Trying to rearrange this to make a new magic square, that would be another task later on. What we're trying to do is group things to say this is also a set of 4 numbers on this magic square that makes 34. So that one that we showed you, those 4 in the corner, 16 and 4 is 20, 13 and 1 is 24, add those together also makes 34. So can somebody therefore give us an example of one that they have come up with? Right, come out, you can walk all the way from the back there, okay, that gives us all thinking time whilst you're arriving, okay, you can sing a tune on the way down just to keep us entertained as well whilst we wait for you, okay, I should ask you to sprint. Okay, there's a pen, okay, there's the board, there's the grid, there's your brain, use all of those to help us.
Like make a line.
You can do what you want.
Like this is like most.
Sorry, are you educating the board or are you educating these human beings? You don't know? Okay, human beings. Turn and talk to the human beings. Okay, you've got to be the teacher. You can stand to one side if you want, so you can refer back to the board, but you've got to tell them, not me, not the board.
I looked at my thing, and every quadrant made like 34 except for this one, because there was two big numbers and 2 small numbers, and it didn't make 34 because he didn't remember to spread the big numbers out. They had to avoid each other, and they had to hide the big numbers.
I've been critical of Albert Dürer now as well. That's quite a challenge. One of the most famous figures of the Renaissance, and you from Bradford, from Rising Hall Primary School, are now challenging it, but that's fine. Okay, that's what we like to see. That's how we make progress. Okay. The reasonable man adapts to the world, the unreasonable man adapts the world to him. And that's what you're kind of doing, that's fine. Okay. So tell me about the square in the middle that you found and how it works.
We found it, there's 10 and 11, which is 21, and then 21 plus 7 is 28, and 28 plus 6 is 34.
Okay, so it's 34, isn't it? Excellent. Okay, thank you for giving us that first one. Excellent. Give him a round of applause. From that one, we'll stick on that, we'll keep on that grid actually, but I'll change the colour of that pen. From that one, can you use something else? Yes, do you want to come out? What's your name? Osman, do you want to come and show us? Okay. From that square in the middle, can you also work out some other things? Okay, have a go.
I closed up on it because first we did 16 for 13 and 11, and I closed up and I did 15 for.
Okay, just hold on 1 second. Okay, that's fine. I'm just going to undo that one. I'll tell you what. We'll move on to another square for that one because I want to relate the previous one back to the square you found. But you can go on and tell me about those ones you found.
Well, 15 and 14 is 29, and 29 with 3 is 32, and 32 are 2 is 34.
Excellent. Okay. See now, when you're criticising Albrecht, putting his big numbers together, not having his small numbers. Well, he didn't them at the top. So he's now got a rectangle, hasn't he, that makes the 34. Well done. Can you, with that rectangle there, can you see what I mean about it being a rectangle?
Yeah.
Okay, if we join those up, it would make a rectangle. Can you use that rectangle and find another rectangle of the same size?
Yeah, if you rotate the square, 5 and 9 is 14, 14 and 12 is 26, and 26 as 8.
Excellent. Okay, so let me just change the colour just to make it clearer as well. So we've actually got that rectangle as well, and as you just said, we rotated it, took it and turned it through 90 degrees. It landed there, and that also made 34. Well done, give her a round of applause. Let's see if we can go back to that. So we've got a square there, and you used a really interesting term. You said quadrant, okay? The quadrant being a square of 4 squares in it, okay? So of the squares of squares. So can you say if we can use that square again in another place by translating, by moving it, by getting it in another position? Yeah, go on then, come on. This young lady here, come out. Let's give you a colour to draw with. Stick with the orange this time. Can you find me another square of exactly the same proportions that will find another one? All the way around with these pens. Depends on what board you use in school, doesn't it? Okay, so yes, and stop. Don't go anywhere, step back now. Okay. Okay, you've got a smile on your face, which is a good start. Okay, so that's the same size square, isn't it? So like we've taken that one off and put it back on here, and it now contains 9, 6, 15, 4. Tell them how it makes 34, or if it does make 34. Tell them how it does it.
15 plus 4 is 19. 19 plus 6 is 25. 25 plus 9 is
34. Perfectly good. Okay, any sequence that you want. I might sometimes go 6 and 4 is a bomb for 10 there. Okay, and that's 24. So we've got 24 plus 10. But there's always other ways of looking at it. Okay, you can go back down. Right, we've got 3 more squares of exactly the same size on that grid that we can put on as well. Okay, you want to have a go? Use the same pen colour. Bit of a steer I gave this time, so don't always do. I usually wait until you discover it and tell me about things. I gave you a bit of a steer by mentioning the wonderful word of quadrilaterals, and mentioning some quadrilaterals. Then people immediately started to explore to try to find some of those quadrilaterals if you've got the teeth in. Now, who could find for me, put onto the screen, a kite? Because I've seen kite in more than one place. Yes, do you want to come out and draw a kite for me, please? Okay? Quick. It's Harris, isn't it? Yeah, okay. So you can bring your sheet with you if you want, if that helps you. Because there is that balance, isn't there, between having something there to help you and having to hold it in your brain. And then, as soon as you're standing in front of an audience, things tend to tip out of your brain, as you noticed today, because I forgot to write number 7. Okay, draw me a kite. It doesn't need to have a pretty picture on it and tails and things like that. All the way around with that pen. That blob there, that one there, that one there, and that one there. Excellent. If I just pinch the pen just to help reinforce it for anybody who's not seeing that, that's 4 circles. Some people see it as a cross, okay? But also we can see it, if we want to, as a kite by joining up the centre of each one of these to make our kite. By joining up the centre of the boxes there, you can now begin to see the way this works on that one. Okay, you can see now it is a kite, isn't it? Okay, very quickly, we normally spend more time on this. Two opposite angles equal in size, two sides in equal in length, two sides equal in length, one pair of opposite angles that are not equal in size, blah, 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 blah. Okay, so that's a kite. Okay, can you prove to them that it makes 34, please?
15 and 11 is 26. 5 and 3 is 8, 26, and 8 is 34.
Okay, very sensible approach that a lot of people are doing is making two pairs, working on those and then regrouping those pairs. Perfectly sensible, but can anybody spot anything that can help you even better with the 15, 11, 3 and 5 that might make your life a bit easier on that example? Yeah?
15 and 5.
Thank you very much. Okay, 15 and 5 makes a nice juicy round 20, doesn't it? Okay, so then you've got 20 and then 14, so it's a little bit easier to regroup after that, isn't it? Okay, fantastic. Give him a round of applause as he goes to sit down. We'll slightly again, and what we'll do is now we'll change the colour. Who can find the vertices for me of another kite? The thing about this is, once you've found one, you can then translate it, pick it up and move it along, or you can rotate it, okay? For example, do you want it's Elias? Elias, yeah, okay. Elias, nearly. Okay. Right, that'll do me for now. Okay. So have we got finding the vertices of another kite? So you've just gone crazy there, haven't you? Because Elias has just rotated and flipped. Okay? Okay, so he's translated and rotated, sorry, because he's taken that one, hasn't he, and rotated it and translated it down to here. Okay? So we can see the 4 vertices from that one. We could rotate the whole one there and have its vertices here. Same 2 numbers at the top and bottom, but changes the other 2 vertices. And then we can take this one and rotate it as well. That's fantastic, sir. Thank you very much. Okay, now one other little point. I tell you what, I shouldn't have let you sit down yet, but you can say it later. Tell me how you would add those 4.
14 add 6 makes 20, and then the 12 on the shoe makes 14, so it makes 34.
Ah, that's interesting. That's exactly the same as we did last time. 14 and 6 is 20, plus 12 and 2 making 14. So we've got 20 plus 14. We had 20 plus 14 before. And actually one of the tricks and techniques for when you start to explore further on this is as you start to struggle to find the next one, find a couple of numbers together. What do 6 and 7 make?
13.
What 6 and 7 make 13. Okay, so if we've got 13, okay, what do you need to make 34? What do you need to make 34? Okay, so we've got 13, we need 21. Well, up above there is 21, isn't it? So that was our middle square. Can you find another way of making 21? Think of another way of making 21 with 2 numbers. Okay, so 10 and 11 make 21. What about 9 and 12?
Yeah.
Okay, oh look, 9 and 12 are on the same row, and that makes a set of 34, doesn't it? Okay? What about 8 and 13?
Yeah.
Okay, that's interesting. So now we've got a kind of weird L shape over here, and that's our trapezium, okay, or a trapezium on there. So if you find a pair of numbers, you can then work out what you need left over and find ways to make that with 2 other numbers. Or you could do it with sets of 3 numbers and work out what's left, okay, and see if you can find another one. But 2 numbers I find works really effectively. Find a pair, work out how much you've got left to get to 34, and then work out the possibilities. So for that one, we were looking for 21, so we had 10 and 11, and then I kept subtracting 1 and adding 1, and I could create my set, couldn't I? So I could go and see if I could find those on the grid. Once I found them on the grid, I could then include them in my sets. So it's just other ways of looking at things. So hidden in there are loads and loads and loads and loads of examples. Like I said, there's parallelograms. You've just seen a quick sketch through of the trapezium. What I'm hoping you'll be able to do is when you go back to your schools, you'll be able to take these notes back, and then you'll be able to teach some of this to other people in your class. The one I think you might find easiest to teach is to help them to get their own magic square, their own 3 by 3. You might be able to do that. And then you might be able to help them understand that there are lots of patterns in here. If you gave that to another member of your class and said, there you go, find out about magic squares, what would they do?
They just copy.
Well, they'd copy it and they wouldn't have any idea what they were copying, would they? Because they're your notes for you, aren't they? Okay? What you'd have to do is use your own notes to be able to explain. So it might be you just demonstrate some of them if you've got time, or it might be you help them to do the exploration as well. So hopefully you get the chance to do that. If not, you might just get the chance to take them away and see how many of those different patterns you can find and present them back to your teacher. can I say thank you very much? You've all worked extremely hard this afternoon. Your responses have been excellent. You've all been an absolute credit to your school, and even your teachers have been a credit to your school as well.